All right, let's see here. Yep, it's working. So you guys excited about the weekend? Are you guys excited about the weekend?
Oh yeah, I'm excited for Wednesday. Ready for class on Wednesday?
Yeah. Let's see here. All right, come on, top hat. $54.59. All right, I will begin with a word of prayer. Ahem. Dear Father, we thank you for this day. I thank you for these students. Just pray that you guide our steps today. We also think of the people in Florida who are recovering from the hurricane. We pray that the Christians in Florida would be able to serve those people in need, that you'd be able to that they'd be able to see your love in the actions of those Christians there, Lord. In your name I pray. Amen. So today we are talking about graphing polynomials. So let's get to it. So the first question is, what is a polynomial? So f of x equals an x to the n plus dot 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 plus a2x squared plus a1x plus a sub 0 is a polynomial. Poly meaning many. So this is many terms, polynomial. Now here, if a sub n is not equal to 0, then the degree of the polynomial is equal to n. So the degree of the polynomial is the highest power that appears in the thing, all right? Non-trivially. And most of our work today is going to be guided by a particular theorem, which is called the Factor Theorem. The Factor Theorem, what does it say? It says given polynomial f of x, all right? Here's the deal. X minus c is factor of f of x, all right? If and only if f of c is equal to 0, all right? Which is also interchangeable with c comma 0 is X-intercept of the graph. So this is the Factor Theorem. This guides much of our thinking in this lecture. All right, the Factor Theorem. There's also a little theorem. So this is a tiny theorem. And it says that the Y-intercept is f of 0, which, by the way, is equal to a sub 0. If it's in, so we talked about that last time, right? So the last class we spent our whole time graphing n equals 2 case, right? Quadratic polynomials. The graph of a quadratic polynomial was a parabola, right? So we learned all kinds of stuff about how to graph parabolas last time. And parabolas are special, right? Because we have formulas for the vertex, and we know things about the parabola because we can complete the square. And And analogs of that algebra don't quite exist for higher order polynomials. All right? But this much we can say. There's a kind of big picture. There's 4 big pictures you can think about. All right? So either the graph looks something like this, or something like this, or something like this, or something like this from a million miles away. In other words, if here your degree of f of x even, here we've got degree of f of x even, degree of f of x odd, right? The degree of f of x odd. And what else do I get to say? What's the difference between these different cases? This is even with a sub n positive. This is even with the leading coefficient negative. This is odd with the leading coefficient positive. This is odd with the leading coefficient negative. So these 4 pictures are what the graph y equals f of x looks like for a polynomial if we're a million miles away. This is the global behavior, the large-scale behavior of our examples. We should be looking for these kinds of patterns in our examples, okay? Now, there's an algorithm. So here's the method. Method to graph. Step number 1, you factor f of x completely. Be careful to group any like factors together. That's step number 1, factor f of x completely. Step number 2, make a sign chart.
What do you mean, be careful to group any like factors together?
Oh, we'll see that in examples. So make a sign chart for f of x. So here, I'll come back to your question, but it'd be a bit. Make a sign chart for f of x where we lay down, you know, C1, C2, all of them, however many there are, CR, where C1, C2, CR are the X-intercepts. Right? And how do I know what the X-intercepts are? I know because I know the factor theorem, right? So every factor in the factorization corresponds to an X-intercept in our thinking today. Okay? And then step 3, oh, and then of course you have to add pluses and minuses as appropriate. We've already talked about that, actually. And then 3 is graph. So that's the method. So because you asked about that, Francisco, I will make my first example involve that issue. Let's see here. So I'm going to try to focus our attention for maybe the first 3 examples, really on steps, mostly on steps 2 and 3. We'll do a little bit on step 1, but there is a tool in our toolkit which we have not yet really gotten out and used yet in here that we will by the end of class today. So after example 3, we'll get to that one. Example 4 is going to be harder, is my point. Example 1. Suppose we had f of x equal to, oh, I don't know, x squared minus 1 times x squared plus 2x plus 1, all right? And then x minus 6 quantity squared. So is this factored completely? No, it's not. We can factor. So x squared minus 1 factors to x plus 1 times x minus 1. X squared plus 2x plus 1 factors to x plus 1 quantity squared. And of course, we've got our x minus 6 quantity squared. All right. Now, this is what I was talking about. Group any like factors together. So we have like factors here, right? We've got like x plus 1 once, then twice over here, so we get cube on that one. And then, of course, we got our x minus 1 and our x minus 6 squared. Once you've factored completely, you can identify the x-intercepts. What are the x-intercepts? I heard x-intercepts are -1, +1, and 6. Very good. Those are the critical numbers that we're going to put on our number line. So number line, like so. Put my -1, my 1, and my 6 over here. All right. And so here we're looking at the number line for f of x. So how should we proceed? And now about half of you are totally lost at this point. I know this because I graded test 1. And we're doing the same thing that we did before with test 1, right? So just checking my mic. But so we need to put pluses and minuses on this, right? So here's a good way to do it. We can always start from the most rightmost thing, okay? And so what is the leading term in this? 6, right? I've got an x cubed from this one. I got an x from that one. I've got an x squared from that, and then lower order stuff, right? So basically, you're looking at, like you told me, x to the 6th plus lower things. So that means that if x is very positive, like x is a billion, that x to the 6th term dominates, and it makes the whole thing plus. So we got pluses in the rightmost. We start with pluses. All right? Then the question is, do we flip the sign or not, right? So we have x minus 6. It's got a square. So we do not flip the sign. We stay positive. Yep.
When you're going to flip, so it's like the 1 and the 6.
Oh, no, it is not the 1 and the 6. It is the 6. The question is, going across 6, do you flip or not?
Always go from like the right. Then
You could, I mean, you can go whichever way you want, but you need information about where you're starting.
okay.
Like if you think about a large negative number to the 6th power, that's also positive, so I can put pluses over here, right? So,
Because you're starting on the right of the 6 and going over, and you only look at the 6.
yeah, I personally think it's easiest to start on the right because it's easy to think about, like putting a large positive number in and then working that way, but yeah, the only thing that matters is the exponent and also the leading coefficient. So 1 here, that's x minus 1, so we're changing plus to minus. And just to re-emphasize, so and also here at minus 1, which is corresponding to this x plus 1 cubed, we also flip again because it's an odd power, so we cross from minus to plus.
If that was a negative 1, to the cube, you would do negatives, right?
If I had negative 1 to the cubed, it wouldn't have changed anything. I mean, if I had x minus 1 cubed, it would be the same. If I had a cube here, same sign chart. Not a thing would change.
Why?
Because it's still odd. So you still change from plus to minus for an odd power. If you had like a square here, then this is not compatible with that. But let's focus on the problem that's at hand here. So that's the sign chart. Once you have that, we can graph. Right? What's the y-intercept? F of 0, right? What is f of 0 equal to here? I mean, you can't just read it off like my starting statement, right? We don't have the standard form. We haven't multiplied it out, nor do we want to multiply this thing out. Do you? I don't. So it's easy though. You just plug in 0. You get from this. I mean, you can plug in 0 to the original formula or the simplified formula, whatever. I'll plug it in the original formula. I gives minus 1 times 1 times minus 6 squared, mind the square, and that gives me what? Minus 36, right? Now that's good news because that is consistent with our number line. See, because the number line had minuses between minus 1 and 1. That's where 0 lives, right? 0's in there, and that's where it's negative. Our y-intercept is negative. Good. So if you doubt your number line, you can always plug in some points and check, right? So here's my x-intercepts. I put down my x-intercepts, and then I just follow the number line. So I start out positive, right? What happens at 6? We bounce. Bounce. And what happens at 1? We're crossing, right? And what happens at minus 1? Well, we're crossing again, right? So we go like that. So there you go. That's the graph. Again, to reemphasize, even powers, we bounce. Odd powers, the graph crosses. That's the pattern. Now we actually, I said bounce and cross in my language before, talking about the nonlinear inequalities, but it really was inappropriate at that point. What am I, bounce, what are you talking about bounce? Now you can see the bounce, right? It's bouncing off the x-axis right here, right? So, and also, because we did that calculation, I can tell you that that point is at minus 36, which goes to show you the, the scale on the y-axis and the x-axis is not at all the same. And I actually have not been careful here, right? Like, I don't know for certain that this turning point is here. I don't know where that turning point is. It could be over here, it could be over there. Like, I don't really know where the turning point is. I know it's somewhere between 1 and 6, because it has to come back down to cross through 1, logically, right? And polynomials have graphs which are continuous, which means, like we were talking about, you have to be able to graph it without lifting your marker, right? So I'm forced to draw this with those x-intercepts. Yep.
In the original number line, could we just plug in 0 to begin with, or is that not recommended?
You could plug in 0 to get started there. Sometimes that works. Yeah?
Is it recommended, because that's what we did for last unit, with like all the factoring stuff. And
Well,
like
it works until it doesn't.
Oh,
Yeah, you know where I'm going with this. Okay, so x plus 10 squared. All right, x cubed. So, and then let's say times x minus 4 times x minus, 8. All right. So this one is a little bit easier than example 1 because what? It's already completely factored, right? So we just need to make our number line. We have x-intercepts where? Yeah, minus 10, 0, positive 4, positive 8. Make your number line. Minus 10, 0, 4, 8, right? And let me mess this up just a little bit, guys. Let me stick a minus 2 in front of the whole thing. All right? Now, some of you are going to ask me, where did the minus 2 come from? The answer is, I just made it up. Okay, this is not, it's just me changing the example ever so slightly to try to illustrate a point. All right, so I put a minus 2 there. What happens? That makes our leading, I mean, this is going to be, minus 2 times, this gives me an x squared, times x cubed, x to the 5th, 6th, 7th. Minus 2x to the 7th is like my leading term then. So with that leading term, or this formula, however you want to look at it, if we start from the right, do we start with minuses or pluses in this case? Minuses, right, because of that minus 2. So if you think about putting in a million or something, it's a really large negative number. So we start out with minuses. Now, how about we get to minus 8? Excuse me, we get to 8, corresponding to x minus 8 by the factor theorem, right? So then we switch minus to plus. We get to 4, again, odd power, power 1, switch to minus. We get to 0. Oh, it's again an odd power, so we flip again. right? And then at minus 10, oh, that's a square, so it bounces there. So we stay plus like that.
Wait, how did you get the leading coefficient?
The way to get the leading coefficient is you pick the biggest, baddest thing from each one of the factors and multiply them. So what is biggest in x plus 10 squared? It's x squared. That's the largest power there, right?
Yeah.
The largest, well, x cubed is x cubed. That's just got an x. So I just multiply the leading term in each factor. So like I've got minus 2 x squared, x cubed, x, and x. If I keep the leading term from each one of these pieces.
Okay.
And so that gives me a 5, 6, 7.
And you're using
Yeah.
that and just plugging in like a bigger number to
I'm
furthest to the right?
So I don't absolutely need to do that. I'm doing that as a safety measure to check my answer. In the previous example, this one, right? When I did that, I had an x to the 6th, right? So what that means, what I should expect from my answer is that if I take a million mile away look at it, I've got like a bowl going upwards. See, because I'm in even case with leading coefficient positive, right? So it should look like a bowl which opens up if I ignore the local behavior close to the origin. So this is a bowl that opens up. That makes sense because I have like x to the 6th as my leading term. Here, what I'm expecting is something that from a million miles away, it should look like this once we get done with it. That's what I'm hoping to see. If I don't see that, I've got an error somewhere. So I need to go back and, think about my life. Think about the choices that I've made, those kinds of things. Let's see here.
You know that the 8, what was passive was negative without plugging into it.
If you plug 1,000 into the formula, you get a negative number easily seen.
All right.
That's all because of the leading coefficient.
I mean, it's because this minus 2 is here. So if I put a big number into this, all of these are positive, 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 positive. But that's negative, so the net is negative.
How do we know it was like what was past the 8 instead of the 4 and the 8?
I want to choose a number that's larger than any of the zeros so that I don't,
Oh, but what like, how do we know that it's negative? And not like how do we know it's not inverted and that's positive in between the 4 and the 8 is negative? That's what I'm-
because if I'm past 8, right? I mean, I'm plugging in a number. I'm thinking about this case here. So I'm looking at numbers larger than 8 for this case, right? So like 1,000, for example. If I plug in 1,000, 1,000 squared, 1,000 cubed, 996. Okay, it's really 1,000, approximately speaking. 1,000 minus 8. I mean, it's positive, it's positive, it's positive, it's positive. The only thing left is that negative. So plus, 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 minus is a minus when I multiply them.
I get it now. Because you go 7.999 minus 8 is negative.
Right, but that would be over here.
Yeah. It's,
Yeah.
Got it.
So my point to you is that we can, without much thinking, you're thinking too hard, without thinking, you could figure out whether it's plus or minus on the right most extreme by just looking at the leading coefficient. If the leading coefficient is positive, it's pluses. If the leading coefficient is negative, it's negative.
Okay.
The rightmost case, the absolute rightmost case for these. All right. So I put my x-intercepts, minus 10. Yeah?
And then you just do the power?
Once I have the x-intercepts, then I follow the number line and make my picture. So I start out positive. I mean, you can go left to right or right to left. Want me to go left to right this time? I've been graphing right to left, but either way, it doesn't matter. So I have to bounce off the 10. Bounce. And what happens at 0? I cross, right? So I got to come back down. I cross through 0. What happens at 4? I cross again. So I have to come back up to cross through the 4. And then I have to cross back again, and then it keeps going down. And so there you go. That's the graph, y equals f of x. Again, from a million miles away, it looks like this. What's the y-intercept?
0.
0, yeah. So there's no y-intercept to figure out here if you want to.
So you're not going to ask for specific points on the graph that are not intercepted.
I don't have to. I mean, you can always add more points to make it more quantitative and less. So this is, I would say this is pretty quantitative in as much as the X behavior is concerned, right? Like it has a pretty good accounting of where the graph is in terms of X. In terms of Y, totally sketchy. I really have no sense of scale whatsoever. It's just capturing the plus or the minusness, if you will, the polarity of the graph in terms of the vertical. To make it better, yeah, I'd have to add some points to add scale, but I don't want to do it for these examples. Yeah. So this is exactly the nonlinear inequality problems, yeah? What's the difference? Now we're making a picture. But like the algorithm is exactly the same. Completely factor, find your critical numbers, which we're now identifying as X-intercepts, right? And we make a sign chart, and then the new thing is, of course, we're making a graph. And so for the graph, when we have an even power, it's bouncing. When we have an odd power, it's crossing. So, and that should also reinforce the idea we go from plus to plus or minus to minus, or change from plus to minus at the cross, yeah?
You're saying like the positives like are bouncing, but like with the 4, it's crossing because the ones next to it are going.
No. Pluses on, so it has to be plus on both sides to bounce. Or it has to be minus on both sides to bounce. Let's do another one. I'll try to go a little bit faster through this example. Example 3, we could have y equals f of x equals to x squared minus 6 quantity squared. Here's a different one. And so how do you factor this? See, this is x plus the square root of 6, x minus the square root of 6. All of that is squared, yeah? So how do you square a product? You square the fact. So this is literally x plus the square root of 6 squared, x minus the square root of 6 squared. Do you want me to make this one a little bit more interesting? This has only got bounces at the moment. You want me to add a cross to it? Make it more exciting? Sure. Or just should I leave it bouncing?
Make it interesting.
Make it interesting, all right. So the solution, you're already lost? I just multiply by x. There. Now I've at least got one thing that crosses. So what are my x-intercepts? Minus root 6, yeah, minus root 6. This one gives me 0, right? And plus root 6. Now both the plus and the minus root 6, they come with a factor which is squared. That means the graph is going to bounce at those x-intercepts. In contrast, at 0, it's just from x, which is the power 1, it's going to cross there. So that's really all we need to make the graph. I guess, oh yeah, I'm sorry. I mean, technically, you can, once you get good at this, you don't really need the number line, but let's do it because I want to enforce that idea. Part of this is I want to kind of help you guys fix your test 1 mistake so that when that comes back up on the final, it's not like a big deal, right? If you got this problem wrong, you can fix it. Okay, so do we start pluses or minuses for this one? Pluses, right? Because if it's the leading coefficient, it would be like x to the power 5.
Oh, you're trying one side.
Stuff. So we got pluses here. We bounce, so we stay plus. We switch at 0. We flip from plus to minus because it's x. And then we stay minus over here again. So this one I think helps with your question. You're asking me.
Wait, why is the negative? Why do we stay?
Because it's x plus the square root of 6 squared. So that means we maintain the sign going across that x-intercept. So the minuses or the pluses is not why it bounces. The fact that there's minuses on both sides or pluses on both sides, that's what speaks to it being a bounce. And the way those are coming from is again from the power of the corresponding term being even, corresponding factor. So my intercepts here are minus root 6, 0, root 6, and so it's bouncing, it's negative, it bounces, woo, and then it crosses, right? And then it bounces, and then it keeps going like this. So that's the graph. Something like that. And again, that makes sense. X to the fifth is my like leading term, so it should look like, you know, the cubic that just goes up and up a million miles away. That's the right shape. I can't really tell you where these humps are without further, you know, investigation of the formula, but there's a picture. Does that help? I hope that helps. All right, so up till now, it's all been fun and games. These are relatively easy examples. Let's do one that's hard. These are actually pretty moderate to, every one of these is a pretty decent test question, actually. That's about more or less where I want to be test-wise, these problems.
What we're doing next isn't on the test.
No, this one would be on the test, but this would be more of a challenge. This would be more like a separate my A's from my B's kind of problem. But, what's that? All I'm trying to say is, every problem is a planned and wanted problem in here. What? Who created math? Well, God, of course. Let's see here. It's a silly question. Let's see here. Example 4. All right, so here I need some help. All right, so I gotta make something up for us. All right, just give me a second. Everybody top hat it already? Ah, yeah.
You're gonna use a program.
Don't get used to don't get used to me, you know, asking you. Let's see here.
Are you gonna use a program to make a graph?
I'm going to use a program to multiply a polynomial for me. Let's see here. Sorry, I'm thinking. I want to make sure I make this example right, otherwise it's going to cause us pain and suffering.
More?
All right, here we go. So we want to graph y equals x to the fourth minus x cubed minus 11x squared plus 9x plus 18. But the good news is we're given a hint. And I'm going to call this thing f of x, okay? Our hint is that f of 2 and f of minus 1 are interesting. Graph. What does interesting mean? So what you're going to do? What you're going to do with that information? What would make sense to try? How about maybe we should try calculating f of 2 and calculating f of minus 1. What happens when we plug in 2? What is f of 2? 2 to the 4 minus 2 to the 8th minus 11 times 2 squared, right? Plus 9 times 2 plus 18, which is what? Let me write that out. That's 16 minus, oh, 2, excuse me, 2 to the third. Yeah, thank you. That was 8, minus 8. Yeah, thanks. Minus 44. Plus 18. Plus 18, apparently. What you got there? You got yourself 36, 46, 52, 52 minus 52. I believe you got 0. 0. What is f of minus 1? So you got 1 minus a minus 1 minus 11 plus 9 times minus 1, right, which is minus 9, plus 18. So just be careful to square the minus and to cube the minus correctly. What's that work out to? So here you got 2 plus 18 is 20 minus 20. So 20 minus 20, also known as 0. Aha. So then what? What does this mean? We know that f of 2 is 0 and f of minus 1 is 0. What does this do for us? How does this help? That tells you that those are x-intercepts, right? But that, more to the point, means that x minus 2 and x plus 1 are both factors of f of x, right? Which means that the product of them is also a factor. So like this is x squared minus x minus 2. This is a factor of f of x, right? What does that mean? That means that you can write this f of x as what? As, you know, x squared minus x minus 2 times something. Right? That's what it means for it to be a factor. What is that something? How do you find the something? Yeah, I mean, you could start poking at it and figure out some things like, well, okay, fine, it's got to have an x squared in it, and it's probably got to end with a plus 9, I mean minus 9, because you got that 18 there. You could do those things, but there's a better way. A way without thinking. So let me show you that way. So how to figure out the something? The way I would recommend doing it is with long division. So here's how that goes. Let me give you a walk down memory lane here. 300 divided by 12, how's that work? Yeah, 12 goes into 3 non-times, no, not at all, right? 12 into 30, well, twice, right? So you get 24, you know, subtract that, you get 6, bring down the 0, 5, then you got, you know, remainder 0. What's this all mean? This means that 12 times 25 is equal to 30. 300 rather. Right? Now, you don't usually look at it that way, right? Like a lot of times when you're doing long division before, how would you have looked at it? You'd have looked at it this way, right? 300 over 12 equals to 25, right? But it's better for us to look at it as 12 times 25 is equal to 300. That's what it's telling us. It's telling us that if you factor 300, where one of your factors is 12, the other factor is 25. We can do the same thing with the polynomial, using what's called polynomial long division. Let's do that. So here we go. So I'm going to put the f of x here, x to the 4th minus x cubed minus 11x squared plus 9x plus 18, right? That's the analog of 300 for us. We're trying to figure out how to fit the factor of x squared minus x minus 2 into that thing. All right? Now, the way that long division of polynomials works, it's pretty much the same as it works with numbers. How many of you, well, let me not, don't tell me. I'll just say this. Let me just make a statement. If you were not taught long division of numbers in elementary school, I'm very sorry. I have to say you're cheated. There are some places that are not teaching this anymore, which is unfortunate. Yeah.
Would that come out to be?
Yeah. Your expression of what I approve of. I feel the same way about it. All right, so here's the deal. We have to figure out what to put up here so that when we multiply by this, we recapture this x to the 4th. So the thing to put here is x squared. Okay? Now x squared times the dividing polynomial gives me x to the power 4 minus x cubed minus 2x squared. All right? And I'm going to put some parentheses here because the minus goes with everything, okay? Now, something pretty cool happens with this example. The x to the 4th cancels, but lovely also the x cubed cancels. That doesn't always happen, but here it happened, which is going to make this take a lot less time than some other examples. And so wonderful. So we get minus 11 minus a minus 2, which is what? Minus 9 x squared. And then I bring these other things down. All right? You may have been taught a different notation to do long division of polynomials. If you remember the different notation and you are, you know, if it's hardwired into your brain, you have to use a different notation for the long division polynomials, more power to you. You're free to do that. All right, so then what? I want to get minus 9x squared from this. Minus 9 is what I do next, right? Minus 9. So minus 9 times that gives me a minus 9x squared plus 9x plus 18, which is good news because when we take the difference, we get 0. If we did this right, the remainder should be 0. What does this mean? This means we factored it. That means we factored it is what it means. So this shows you that x to the 4th minus x cubed minus 11x squared plus 9x plus 18 is equal to x squared minus x minus 2 times x squared minus 9. So in summary, we can use long division to figure out the other factor that we're missing. If you know a factor of the polynomial, you can divide that factor out of it to see what you're left with. This is a tool for factoring we have not yet talked about in here, right? But this is a significant tool, especially for higher order problems. And so then what? Well, then to come back to our problem of graphing, we need to factor it completely, right? Once you're down to quadratics, then you know you can do it. Because once we're to quadratics, we can fall back on completing the square and our usual bag of tricks. And there's no quadratic that can escape our clutches, right? They're all going to suffer, you know, a complete factorization. We will kill them all. I'm sorry, we will show them that we love them and convince them to join us and, you know, harmonious existence. All right, so let's see here. So what do we got? We got this one factors x minus 2. We know this is where we came from, right? X plus 1. And then this guy is x plus 3 times x minus 3. So now we have it completely. So my point to you is this time, step number 1 in the method took a while, didn't it? Right? So sometimes the factor completely part is most of the work. Yeah? All right, now that we have this, we can make our number line and graph this thing. It won't be that bad. So let's do that.
On the test, will you give us a hint that f of something and the other thing are interesting?
Wouldn't that make it too easy, though?
I'd very much appreciate that.
Yeah, I mean, to be honest, guys, like without that hint, this is not a reasonable problem, right? That hint is non-negotiable for this problem. Without that, how do you factor that? You don't. Well, I mean, okay, fine. Like, it's a book problem. I mean, that's not true. I made it up. But if it was a book problem, usually if you plug in 1, 2, or 3, or minus 1, or minus 2, or minus 3, something in there is going to make it 0. And so you can go from there, right? But that's just an artifact of textbooks making lazy problems. Yeah? Like logically speaking, how do you factor something like this? That's a much harder question. That's a good question.
Where's positive?
I don't think I should have a positive 1 there, actually. I should have -1, positive 2. Yeah, I'm sorry. What are my x-intercepts? Let me read it from over here. I'm sorry, I got lost. Intercepts. Yeah, 2, -1, -3, and 3. Yeah, so I should have -1. I should -3 first, -1 second, then my 2, and then finally 3. Okay, great. Leading coefficient's positive, so I start pluses. Every term here is a flip because they're all odd powers. So I go plus, plus, minus, minus, plus, plus, minus, minus, and then pluses again. My y-axis is up in here somewhere. So my x-intercepts are at -3, -1, 2, and 3. What's the y-intercept? Oh, did you pan over? Okay. So you might have to pan back. The y-intercept is right here. 18, right? It's the constant. Now that wasn't available to us in previous examples, was it? Because, why? Because previous examples I didn't give you in the standard form, right? I gave you factored form, which made the problem easier, except for the y-intercept part. But anyway, so here goes. We go up, we cross again, we cross back, we cross again, and there you go. There you go. There's y equals f of x in this case. -3, -1, 2, 3, and the y-intercept, like we were just saying, is 18. So there is one thing I have hidden in all this, right? Like, there's one issue that we have completely ignored today, and I've ignored it in not just this section, but in the other 2 sections as well, if you were to be so bored as to look at those. But since you guys are the section where I'm awake, let me give you one more example here. Example, where are we? 4? 5. What if you had f of x equal to x minus 3 times x squared plus 4x plus 5? See, this guy is what? That's x plus 2 quantity squared, right?
Yeah.
Plus 1, if you complete the square there. So that one is never 0. So this cubic actually only has one interesting x-intercept, namely 3. So 3 is your intercept, and you're going to be pluses over here, minuses over there. All right? And so when you graph this thing, it crosses at 3, right? And it looks something kind of sort of like that. So that's the other thing that I haven't talked about today, is you can have factors which are prime. And how do the prime factors figure in? Not in any kind of nice way that I can describe elegantly. They just kind of don't factor in, because the prime factors are either always positive or always negative. They don't affect the plus minuses. Okay, guys, so Wednesday, no class, all right? But I will make you guys a worksheet, and I'm going to post a video. And the worksheet, I just want you to like fill in some answers in the worksheet. You'll be able to fill in the answers from the video that I'm going to make. So my suspicion is that pretty much everybody here, with maybe a few small exceptions, didn't understand what I did here, right? So it would probably be helpful if I made you another like half a dozen examples of this, right? So that's what the video is going to be mostly focused, is on how we can do long division and how that helps us factor. I'm going to focus just on that, not so much on the graphing in the video, all right? The other thing I need to tell you, and this is important, in your homework, it says to use synthetic division for certain problems. Everywhere it says use synthetic division, you can cross that out and write long division in place of it, because I will not teach you synthetic division, nor do I expect you to learn it. We can use long division for everything.
Why not synthetic division?
Why not synthetic division? Synthetic division only allows you to